Algebra represents the continuous path of a geometric line by using a discrete set of numbers and symbols. To perform this translation, we typically rely on several different forms: the slope-intercept, slope-point, and two-point equations. These forms are situational. They require specific known variables, like a precise intercept or a second set of coordinates, before the equation can be written. Using these situational tools is inefficient. If the geometric conditions of the line change, the specific formula we've chosen can fail to describe it. Without a unified algebraic language, the study of lines becomes a series of memorized fragments rather than a coherent system. Despite their different appearances, all these specialized equations share the same mathematical origin. They can all be replaced by one singular format, the general linear equation, ax plus by plus c equals 0. This is a linear polynomial in two variables, x and y, where the expression is equated to 0. The only requirement for this format is that the coefficients a and b cannot both be 0 at the same time. Using this unified polynomial structure provides a highly consistent method for representing any straight line in a Cartesian plane. We can see the structure by looking at the standard slope-point form. Independent variables x and y stand apart from fixed inputs. We distribute slope m across the x terms and move everything left to equal 0. Grouping variables with coefficients and isolating constants as a, b, and c reveals the general format. This proves that the situational formulas used in introductory geometry are actually the general polynomial in a different arrangement. The coefficients a, b, and c contain all the information necessary to determine the physical orientation of the line. We extract slope and intercepts directly from these three values. Isolating y reveals the slope-intercept form, where slope is negative a over b and y-intercept is negative c over b. Setting y to 0 shows the x-intercept is negative c over a. These three formulas provide immediate access to the line's physical traits using only its coefficients. Consider a geometric extreme that breaks our standard models. A line that is perfectly vertical, standing straight up and down on the Cartesian plane. Equations that rely on a measurable slope fail here. As a line becomes vertical, the horizontal change reaches 0, causing the slope value to climb toward infinity. Because the slope of a vertical line is undefined, situational tools cannot represent this geometry. The general linear equation is robust enough to describe this scenario. If we set the b coefficient to 0, the y variable is eliminated from the equation. We are left with ax plus c equals 0, which simplifies to x equals negative c over a. This describes a line where every point shares the same x-coordinate, regardless of the value of y, the definition of a vertical line. Since it can represent lines both with and without a defined slope, the general form is a complete model for all linear geometry. We can apply these extraction formulas to a specific equation to see how they function in practice. For 3x minus 4y plus 12 equals 0, a is 3, b is negative 4, c is 12. The x-intercept, negative c over a, is negative 4. The y-intercept, negative c over b, is 3. The slope, negative a over b, is 3 over 4. Every physical attribute of the line has been derived solely from its algebraic coefficients. To verify, we plot the points on a graph. The first point goes at the x-intercept, negative 4. The second point at the y-intercept, 3. The line drawn through them rises 3 units for every 4 horizontal units, confirming our 3 over 4 slope. We have moved from a list of situational forms to a single, robust polynomial that handles every linear case. A linear polynomial in two variables is the exact algebraic representation of a geometric straight line. Mastering the general linear equation provides a precise method for describing structural geometry, a requirement for fields ranging from data science to applied mathematics.